Hello, good morning, good afternoon. This is Alvis Kariajan, and this is the final video presentation of the final thesis at LJMU in AI and ML. And the subject that I've chosen for the final thesis is multimodal recommendation systems using deep learning techniques. So let me straight away jump into the content. First, coming to the aims and objective of this study. Uh, so, uh, the aim of this particular study was to develop an effective recommendation engine for an e-commerce company. As you know, recommendation engine is a bread and butter for most of the e-commerce digital companies. And this is like one of the very heavily researched area in AI ML. So what exactly is like my contribution to recommendation systems? So here in this particular study, we are trying to analyze how an existing recommendation engine performance and accuracy can be improved by utilizing data from other modalities like text data, image data, along with the usual user item ratings data. So that's our aim at a high level. And coming to the objectives, there are like four main objectives for this study. First is to compare different deep learning algorithms, techniques, and architecture for processing multimodal data. So when I say multimodal, data from multiple modalities other than just the tabular data. Second, evaluate the recommendation engine's performance using various metrics and compare it with the single model and hybrid methods. And the third objective is leverage the pre-trained models. For example, BERT and GPT for text, and for image, you are a VGG. There are like visual transformers and so on. So how we can leverage some of this latest pre-trained models and improve our model. And finally, I want to assess the whole landscape, identify the strengths and limitations of multimodal engine and provide some kind of guidance and insights for future scope and research. So those are the objectives. Now, coming to the literature review part of it. So like I won't get into the whole details of it, but at a very high level, there are two kinds of recommendation engines. One is collaborative filtering recommendation engine. Another one is content-based filtering. So as the name suggests, collaborative filtering is wherein the recommendations are based on the past interactions of the users with items. And on the other hand, content-based filtering, the features or the attributes of the items are used to make recommendations. In very simple words, I'll give you a very simple example of how collaborative filtering works. So imagine there are two people, X and Y. Say X buy A, B, C in the past, but Y has bought only A and B in the past. So since X and Y are like very similar, it's very likely that Y also will buy C in the future. So collaborative filtering is as simple as that. But again, there are like different kinds of techniques to implement collaborative filtering. The most popular being singular value decomposition and non-negative matrix factorization. And typically, even though these are the broad level, at a broad level, these are the different kind of recommendation engine. In reality, most of the companies use a hybrid approach where they use collaborative filtering when there is enough data for a user, but for a relatively new user, you won't have any past interaction. That's where the recommendations are based on the item or the features of the items. Um, yeah, and recommendation engine is one of the core product offering for major tech companies. And as I've already mentioned, most of them are proprietary and involves a combination of several modeling techniques. But if you take at a very high level, this is how a typical recommendation engine for an enterprise would look like. It would have three major blocks. So first it will create, it will have a phase called candidate generation. So in the candidate generation, the recommendation engine, what it does is it will identify a set of potential items that a user may be interested, based on very high level filters like demographics or other information. A typical example would be, say, if you're building a video recommendation engine like a YouTube, for Indian market, then the top hit music in India, that would come up under this candidate generation uh, list. The reason being why we need a candidate generation is, there could be millions of videos in the YouTube or any platform, and you cannot process all this data for the recommendation engine and compare each item against a user. That's why we need a candidate generation. That's the first step. In the second step, the candidate items are scored and ranked based on their relevance to user interest. Some additional filters are also applied here, basically government regulations, if something is not safe for work and things like that. And after that, it moves into the third layer, where you have a classifier or a ranker algorithm, which will provide more nuanced or the final list of recommendation for each individual user. So here, all the user interaction, user features, and everything would be assessed to come up with the top n items recommended to each user. Again, given the complexity of the recommendation engine, we will be focusing on the third portion for our study. Basically, how can you improve the classifier or the ranker algorithm that is used in a recommendation engine using multimodal data. Yeah, before we get into the details of the methodology that we have implemented, let me give a brief on the different kind of frameworks used by the top digital companies in the world. As you can see here, right? Netflix, it's not a simple three-pronged approach. They also use different kind of custom algorithms, like personalized video ranker, what is the top end ranker in the region, what is the trending now ranker, whether you have watched a video and stopped it, like then some ranking based on your search. So all of those things will be combined to come up with the final recommendation engine. Since that is like the backbone of Netflix. Similarly, TikTok. Take for example TikTok. TikTok is very addictive, because it always give you the right recommendations to you, almost on a real-time basis. This is attained by having models which run in an almost real-time basis. Again, all of this scope, like dissecting all of them, is beyond the scope of the study. I'll straight away go into the methodology that we have proposed and implemented for the study. So this is the methodology that I proposed for the recommendation classifier. Before I get into this detail, uh, let me discuss the data that we have used for this particular study. So for this data, we have used Amazon Pantry Review dataset. What this data essentially contains is the user item ratings for pantry section of Amazon website. So the data will contain what is the rating on a scale of 1 to 5 given by each user for each item. So along with the pantry data set, we also had Amazon Pantry product metadata. So in the product metadata, we had more metadata details about the items, like what is the image of the product, then what is the description, specifications, brand, etc. about the product or item. And again, we all did all the experiment by having a train test approach, and all the latest purchase made by a particular user was considered to be in the test set, and the purchases made before the latest purchase was considered in the train data set, and we assess the evaluation metrics on the test data to see how our algorithm is working. And again, this data set was pretty huge. It had like 137K item ratings. It had data about 14,000 reviewers and more than 4,700 items. So we were not able, like I was not able to process it in my local system. So I had to use a Google Colab machine with GPU. Since we are using a deep learning approach here, the process was like fast tracked using a GPU. Yeah, and coming to the methodology, as you can see in the figure, this is the high level approach that we are using. So first thing, we are taking, unlike other traditional algorithms, we are taking uh, features from all kind of data modalities. For example, using our text processing module, we are taking the details of the uh, item descriptions, item brand, and so on. Using image processing module, we are taking information about the product image. Then using the tabular processing module, we are basically taking the product user interaction data, or basically the ratings data. And all of them is like combined, all of these features are combined together and then fed into deep neural network to come up with a relevance score. Relevance score in the sense, what is the relevance score for a item for a user. So this output was generated, and once you have the score, you can arrange each of the item for each user based on the score, and now you'll know what are the top items that a particular person is or user is very likely to buy. So this is again the approach at a very high level. If you get into the implementation details, so as you can see, for processing images, we have used a pre-trained model called VGG network, and for processing the textual information like the product description and all, we used uh, uh, BERT, a transformer-based model to get the features. And user we have used embeddings in deep learning network to get the user item interactions, and all of these features were like fed together into a deep neural network of layers 256, 64, and 32. And finally, the last layer in the deep neural network will give you the relevance score. So this is what we have done, and we have, as a loss function for this project, we have used mean squared error as a loss function. This is again, we are predicting the relevance score, so we could have used binary cross entropy loss also, but since we had the ratings on a scale of 1 to 5, where like a person is more likely to buy 5, then we thought that it will be more appropriate to MSE, and also based on our experiments, we found out that MSE was working better than the BSE loss function. Yeah. Then coming to the data processing for modeling, again, this is something that we wanted to call out. I use something called negative sampling in modeling, or in the pre-processing step before we feed the data into the model. So there is like one problem with our data. Our data had only positive or implicit interaction, right? Basically, if someone rates an item, then that means the person has purchased it. So you don't have interactions where the person has not purchased it. So if you want to predict the items that a person is going to purchase, then you should also need the negative interactions, the cases where the person did not buy. In order to do that, we did something called negative sampling, where we artificially created a subset of negative sample for the trading. So here what we have done is, for each positive interaction, for each say a user rates an item A, then you will create 4 other sample where the rating is 0. Basically, user user A with item B, where the rating is 0 because he has not seen the product, where he has not purchased the product. Negative sampling was done, and coming to the data processing in different modalities. So text data, we did stemming, punctuations, stop words removal and all, and finally tokenization so that it can be fed into BERT to get the embeddings information from it. And even for the images also, so we had images of all kind of sizes. Those images had to resized into 224 into 224 into 3 so that it works for BGG network. Then similarly for user item data also, we had to convert it into numerical ID so that the model can understand it. And coming to the effectiveness of the model, so we used something called hit at 10 ratio to effectively measure the effectiveness of the recommendation engine. So hit at 10 ratio is nothing but it measures the percentage of users for whom the correct item is present in the top 10 recommendations. For example, take for example our use case. So if there is a person A and we had around 4,900 items, right? For a person A, if you arrange all the items based on their relevance score and take the top 10 items having the most high relevant score, and if if one of those items in the top 10 was purchased later by the user, then it will be considered to be a hit. Okay, so that again, this is a very popular performance measurement used across for recommendation engines. Similarly, we have used something called NDCG, which is normalized discount cumulative gain. Here, there is like they stress more on the relevance or the uh, uh, relevance and the ranking of the item compared to the actual purchase. So these two measurements were used for evaluating the effectiveness of the recommendation engine. And here are our results. So we have done basically 4 experiments. So we ran the model with just a baseline model, wherein we have not used any image text features. In the second experiment, we used image baseline model plus image features. And the second one, it's baseline model with text features. And the fourth model is a full-fledged model where we have used all the features to come up with the recommendation engine. So when I say baseline model, we use only the user item interactions, and the results are tabulated here. So one thing that is really standing out is we are getting a very low hit ratio. So hit at 10 is like 0.11, which is not that great. So which basically tells that probably this implemented algorithm or architecture might not be working well for this data set, or it could be that it's really difficult to predict the future purchases for pantry items. Even that could be the case. And also, if you look at the different experiments, one thing is that uh, the baseline model, the hit ratio is 0.11. So if you consider other experiments, experiment 2, 3, and 4, there the hit ratio is not very high compared to the baseline model, which suggests that uh, adding other features are not incrementally benefiting or significantly benefiting compared to the baseline model where we use just user item ratings. And one thing also that stands out is in the experiment 2, right? You see the baseline model and image features is uh, giving 0.13, which is like highest hit ratio out of all experiments. Again, this is not very conclusive. We cannot say that image features will always make a difference. But this is what the experiment results have given us. Coming to the conclusion and future steps of this study, again, the conclusion, the study wasn't very conclusive. So adding multiple modalities had minimal, or I would say very negative impact on the model performance according to our experiment. But at the same time, one thing that we have to keep in mind is there is definitely potential in using multimodal data as models combining image, right, outperformed combinations of other modalities. And most importantly, the results can vary significantly. Even for the same architecture, the results could vary across multiple data sets, and by leveraging more advanced pre-training models. So as far as future steps are considered, we could test it on other data set. We could try different kind of pre-trained models. We could experiment with the architecture and the hyperparameters. We could use a different kind of loss function. We could even think of training, like a pre-training, instead of using a pre-trained model for image and text feature and extraction. We could even build a model from scratch for that. Uh, but again, this will require a lot of computational power. To conclude, yeah, I mean, in the particular data set that we considered, the architecture is not working well, but we definitely see future potential in using the same architecture across other data set, and assessing to check whether it's actually working out or not. So that concludes my presentation. Thanks everyone.